Okay, so good evening, everyone. So we'll continue our discussion from the previous class. So before going into those discussions, so I just want to show few special crystal structures and allotropes that we discussed in the last class. So these special structures are important in the sense they are used quite often in many of applications. So the first one, what you see is so I'll use so the first one here is represents a carbon, the diamond crystal structure. So this is special in the sense it is a FCC structure. But what you have is you have two different set of carbon atoms. So one carbon atom set of carbon atoms, they form one FCC lattice, so which are, let's say, on the corners and then on the faces. So you have one, two, three, four, five, six, seven, eight carbon atoms on the corners, and then you have also four carbon atoms on the faces, on the six faces. In addition to that, you have four more carbon atoms within the unit cell. So which is like this one, then this one, and this one. Okay, so these are not on the face center, but rather they are within the unit cell. So that means the total number of atoms per unit cell when you calculate will be 8. Okay, so this is still a FCC crystal, but this is a diamond, how the crystal structure, how it looks like. So this similar crystal structure also applies to silicon, for example. So silicon also has a diamond-like crystal structure. So you will have in place of carbon, so you'll have silicon, and similarly the silicon unit cell will have eight atoms per unit cell. So then you have also, instead of having same atom, so you can have two different atom 1 and atom 2. So atom 1, for example, will be in the corner and the face center, and the atom 2 will be within the unit cell, for example. So in this case, this represents this zinc sulfide. Okay, so this is also called as a zinc blende structure. Okay, so here you have just in the earlier case you have two different types of carbon. So here you have sulfur and a zinc. So zinc, for example, these bigger ones are the zinc which are within the unit cell, and the sulfur occupies the corners and the face centers. So again, total number of atoms are 8. But if you look at an individual zinc atom, so number of zinc atoms will be 4, and number of sulfur atoms will be also 4. So these atoms which are within the unit cell, so they occupy a special position. Okay. So normally the way to find out their index, like we saw earlier, so how to find out the indices. So the position or the coordinate of this atom, you can find, let's say if you say one atom is, take the corner atom, for example, 000. So the special atom that is within the unit cell will be displaced along one of the body diagonal axis by this one fourth of the distance, one fourth 0 0. So that is a typical position of this second atom which is within the unit cell. So this special structure is a kind of quite observed quite often in many materials. Okay, so as I said, diamond, silicon, then this zinc sulfide, then gallium arsenide. So many semiconductors, they have this special kind of crystal structure, and this special structure leads to their special electrical characteristic. Okay, the another point which I discussed, but it was not elaborated, this allotropes of carbon. So when we talk about allotropes of carbon, I said one is graphite and the other one is diamond. Basically, naturally, that you what you see. Then there is also this fullerene, which is also observed, produced in the lab, and you can also make a unit cell out of it. So in the last class, I discussed this layered structure of graphite. That is what I wanted to show here. So you have this sp2 hybridization along this hexagonal plane, so which leads to this hexagonal structure or hexagon type arrangement. Okay, and along this axis, so this will be your A and B axis, so to say. Along the C axis, so you have a very weakly bonded carbon atom, which is just a van der Waals bonding. So within this plane, so the carbon-carbon bonding is a covalent bonding, sp2 hybridization. But out of the plane, along this direction, you have a very weak van der Waals bonding. So it is very easy, normally, therefore, to remove one of the layers because the van der Waals force is very weak. So you can easily remove one of the layers. And if you able to isolate only one such layer, so that what we call as a graphene. Okay, so 2D material, so it is just like a 2D sheet, so we call it as a graphene. So here, this is an example of another allotrope of carbon, which is made up of fullerene. One fullerene is a molecule which has 60 carbon atoms, and then these 60 carbon atoms as a molecule occupy, for example, here a FCC. They form a FCC unit cell. So this is another form of a crystal of carbon. So there is also like carbon nanotubes and other forms which is not like, if you really go into the nanostructure and its application, so it'll be you will learn about that. Okay, so another form that we also talked about briefly towards the end is the different form of crystalline material that we see. So one is what we call as a single crystal. So the this is a schematic like representation of this single crystal material. So what you see is atoms are perfectly ordered, arranged, so there are no deformation, no defects, nothing. So all the atomic positions are occupied, and well defined planes, well defined orientation. So this is what you call as a perfect crystal or a single crystal. But naturally, what happens when you make a crystal? So most of the time, what you have is something as a polycrystal. So that means you nucleate some a single crystal, so to say, and this single crystal will be nucleated at different places. Okay, so when you are let's say condensing from a vapor phase or a liquid phase within a vessel, so to say, so there will be different locations where this nucleation will happen, and those nucleus will be like a one small crystal or one small unit cell. So the square you can think is like a unit cell. So now that unit cell will grow, and it will grow in any random direction. Okay, because the process is random, so it will grow in random direction. And when they grow and eventually meet, that means you form finally the solid material. So they will form this different orientation. So it is, if you look at one particular region, it looks like a single crystal, but when you move across, so the orientation changes. Okay, so the atomic planes are now oriented in a different direction, and this is what we call as a polycrystal. Now this boundary that separates these crystals are called as a grain boundary. So you have, this is what you within one within a boundary you call that is as a grain, and two grains are separated by a boundary, what you call as a grain boundary. So look at this grain boundary in a more detail. But the interesting part about the grain boundary is it is a highly energetic region within the crystal, because there are incomplete bonds, there will be broken bonds. So the energy compared to within the crystal will be much higher in the grain boundary. So you will have many interesting interfacial features that will arise at the grain boundary. So many of the impurities, or we'll discuss about some of those imperfections or defects, so they will be observed only at the grain boundary. This we already discussed, as I just said. So the formation of a crystal. So you have a nucleation process. So that means, let's say you see this is like represents one unit cell, for example, and this unit cell will grow as your the condensation process happens. So condensation process is typically when you are cooling it down. Okay, so you are cooling it down from a vapor or a liquid phase. Now these unit cells, they will grow, and because normally a process will be where the nucleation is random, so you get this polycrystalline state or grain and grain boundary. But if you want to grow a single crystal, it is also possible, like in this case, like a perfect crystal without this many different orientation. So what you need to do, that means you need to only nucleate one nucleus. So if you have many nucleus, random nucleation, they will always get a polycrystal. So if you want to grow a single crystal, you have to grow one single nucleus. So that is also possible. It is a very sophisticated way to do that. And you can, so normally in order to achieve, so one way to do it, so you have to cool down, or when you are condensing, you condense it really very slowly, so not really fast. So in this process, slow means really slow. That means when I'm saying condensation is happening, that means you are decreasing the temperature. So the temperature has to decrease so that this condensation or the solidification happens. Now you do it so slowly that atoms have enough time. So you can imagine these atoms are all moving randomly. So now if they are cooling down, so they have to settle down. So the this random vibration will reduce, and that's how the solids will form. Now if you want to reduce this random motion and make it stable, but you want to make it in a perfect orientation, so you give enough time to cool down. So typically when you cool down, it will be of the order of like 1 degree, maybe per hour or per few hours. So 1 degree Celsius change in temperature per hour. So that is the kind of uh, temperature rate, change in temperature that you achieve. So for a polycrystalline, so this rate could be like 5 degree, 10 degree Celsius, even 1 degree Celsius per minute. Okay, so that could be the how rapid the change could be. And if I, in fact, so this by controlling this rate of change of temperature, you can even get something known as a amorphous or non-crystalline material. For example, if I do a very fast cooling, so cooling will be like what we call the process as quenching. So quenching means you reduce the temperature from, let's say, 1,000 degrees Celsius. So the something is at a very high in a hot, like in a on a hot furnace, or on a oven, or a heater, for example, so which is maybe around more than 500 or 600 degrees Celsius, and you just take it and put it in water, for example. So that means what you do is something called as a quenching. So in this way, so you just don't allow the atoms to move or rearrange. So they will just freeze wherever they are, and that will form an amorphous material. And that is how glass is formed. This is formed by a quenching. So this is, you get amorphous material by that. So this is an example of this non-crystalline or amorphous phase. So glass, when we talk about glass, it is basically a silicon dioxide. So silicon and oxygen. So you have here the oxygen atoms and the silicon atoms, and you can, if you cool down relatively slowly, so you will get this nice structure, hexagonal structure of silicon dioxide. But if you cool it down or quench it, so you get this disordered state. So it is not anymore a long range order. So here you have a perfect this hexagon which is extended over many such hexagons will be arranged together, so you get a polycrystal. But here what you see, these hexagons are not perfectly formed. Okay, so they have really a short range ordering, but there is no long range order. So that is what we call as a non-crystalline or amorphous material. Okay, so the way, like, we have this different form of crystal, so single crystal, polycrystal, or amorphous. So what is the process, how we can find it out? Okay, so that we know that yes, there is some periodic arrangement of atom is there. So the best tool that we have is called as a X-ray diffraction. Okay, so this is a technique or tool that was used like way back in 1915, 1916, and it is still very useful for initially characterizing or finding out whether your material is it is crystalline or non-crystalline. So what is the crystal structure, what is the lattice parameter. So many things can be done using this simple technique. So this is a very well known tool that we have, and we continue to use when you develop any material. So you synthesize or make any new material or any material that you make in the lab. So you immediately, the first thing what you always do is a X-ray diffraction. So how this X-ray diffraction finds out the crystal structure? So it is based on a simple optical principle, what we call as a diffraction and interference. Okay, so this is a simple schematic to show that. So you have several atoms. So these blue ones represent these atoms. Okay, so you have uh, several atoms which are you have a periodic arrangement right now. So that means it is a crystalline structure. Now, this you can imagine it is like forming different planes, so crystal planes. So you have a plane A, plane B, and maybe another plane A or B or whatever. So it could be same atom, it could be different atom. So in this case, to keep it simple, so you have the same kind of atom, but this represents a plane A, this represents plane B. Now you have an incident X-ray. So this X-ray normally is produced by accelerating your electron, and these electrons will strike a target, and in the process they will emit X-ray radiation, so which is an electromagnetic radiation. And this radiation then will incident on your sample, on your material, and this is how it is now represented. So there is one electromagnetic wave that is getting diffracted or getting scattered by one of the atom here, p atom. So we don't say it is from one atom, but it will be scattered from the plane A, because all the atoms will have the same scattering power. So you'll get a diffraction from uh, this arrangement. Now, why this we are calling it diffraction? Because these wavelength of the X-ray that we are using is of the order of the interatomic distance. Okay, or interplanar distance. So in this case, it is quite same, the interplanar and interatomic distance. But typically, whenever we talk about a diffraction process of electromagnetic radiation, so you need to have the wavelength of the radiation should match at least with the the distance between the scatterers. So you have many point scatterers, let's say. So in this case, these are atoms. Now the distance between these should be of the order of the wavelength of the incident electromagnetic radiation. So this is why we are able to perform this diffraction on atomic, on a material at atomic scale. Okay, so if I want to do with a visible light, for example, so I will take something known as a diffraction grating. Okay, so that is what you use in optics. You make this diffraction grating or slits, and then where the slit width and sizes will be of the order of a micron. Okay, so micrometer, uh, or let's say few hundred nanometer. Okay, so in that case, so this will diffract optical, so light or electromagnetic radiation, the visible range. So that is, let's say, from red to blue. So exactly the same thing, we have a grating kind of thing. We have created a grating, and now the light is getting diffracted. So this is, in this case, light is X-ray. So you have a diffraction from two different planes. Okay, so you have a plane A and plane B. Now these two diffracted X-ray light, so they will then meet. Okay, so this diffracted beam will meet at, when you observe, for example, here, and when they meet, so depending on their phase difference, so they will either interfere and produce a constructive interference or a destructive interference. So that means they will add up, so the amplitudes will add up and give a maximum amplitude, or they will cancel each other out and give a zero amplitude. Okay, so this process, this interference will happen because of the diffracted wave or diffracted light from two different planes. Now, how you know whether for a given distance, okay, this atomic distance, or the distance between two planes, whether there will be a constructive or a destructive interference? So that you can calculate if you know what is the path difference between these two waves. So this uh, the first ray, for example, 1, so it is getting diffracted from the plane A, from atom P, and goes in this direction, we get 1 prime. Okay, so the beam 2, it is getting diffracted from from an atom Q, which is in the plane B, and gives you 2 prime. So this 1 prime and 2 prime will interfere. Now what is the path difference? So if you look at, so what you do is you draw a perpendicular from this point P, okay, onto this parallel beam. So then another perpendicular line from this P up to T. So the path difference between these two, 1 and 2, after diffraction will be given by this distance SQ and QT. So this is the extra path this beam 2 travels after, I mean, when it undergoes a diffraction from plane B or from the atom Q. So it goes or takes a longer path, so SQ plus QT. Now you can calculate what is this SQ and QT. So this is again a simple trigonometric uh, principle you use. So if you use a simple trigonometry, so what you can calculate, this SQ plus QT both will be half DHKL sine theta. So the D here, this D represents the distance between the two planes, so which you call as an interplanar distance. So this is your interplanar distance. Now you just add up, and if it is equal to an integer multiple of lambda, so in that case you will get a constructive interference, otherwise you will get a destructive interference. So if you have a constructive interference, that means you have a maximum intensity. So it will only happen if this DHKL sine theta, so for a given angle of incident, so you are your beam is incident at certain angle theta. Now for that angle, so you know what is the path difference, and if this path difference is equal to n lambda, so we get a constructive interference. So that is what you write here as 2d scale sine theta, that is 2d sine theta equal to n lambda. That is what is known as Bragg's law. So that means if you want to see a a constructive interference, that means maximum intensity after diffraction, so this condition has to be satisfied. uh, but remember, this Bragg's law is a necessary condition, but it is not a sufficient condition for diffraction. So what it means, that even if, let's say, you have a set of planes which will satisfy Bragg's law, so that they may not give rise to a constructive interference. Why? Because your Bragg's condition assumes that the atoms are actually, the diffraction happens from the corner, the atoms which are in the corners. But if I like at a BCC or a FCC, so that you have atoms in the body center or phase center. So they can introduce additional phase shift or a path difference to the diffracted light, and that they can also lead to a different set of, they can now change the condition for the interference. So that's why you have to take into account both the Bragg's condition as well as what are the actual position of the atoms, to understand that where the diffraction will, whether the diffraction will happen and you will see a constructive interference or not. So this leads to as an additional rule, so which is known as a reflection rule, which is quite can be derived easily for cubic crystals. So if I take, for example, BCC, a crystal structure, so if I have a HKL plane, so which represents, so this HKL represents, these are the Miller indices which represent the set of planes that we are talking about. Now, if this H plus K plus L is even, so then only we will have a constructive interference. So Bragg's law has to be satisfied. In addition, you have to satisfy also this condition: H plus K plus L should be even. So in that case, so you will have a reflection from a 110 plane, 200 plane, 211 plane, 220, and so on. So if you add up HKL, they will always be even. Now that means in a BCC crystal, so I will not have a diffraction peak corresponding to a 111 plane. But that rule changes for FCC. For example, FCC, the H, K, and L value either all odd or all even. So that is only you will see. So the Bragg's condition has to be satisfied, plus the HKL value either it should be all odd or all even. Now that gives rise to only allow certain planes, Miller indices, which you can observe in a FCC crystal. So 111, 200, 220, and so on. So this is what like a additional rule you have to remember. So this is for cubic crystal. So you will also have similar rules for other crystals as well. Simple cubic, you will observe all reflections. So there are no rules, because as I said, the Bragg's law. So here the Bragg's law is satisfied, and that is the sufficient condition because atoms are only at the corner of the cube. Okay. So this actually can be useful because if you can identify what are the Miller indices for a given crystal, or if you know what is the so you can say, okay, I see only the diffraction peak corresponding to only either even or all odd. Okay, so either they're all odd or all even. So immediately you know, so the material has a crystal structure which is FCC. But if you see this 110, 200, this 211, for example, so 110 is absent in FCC. Okay. 200 is present in all FCC and BCC. Then 211, this is in BCC, but it is absent in FCC. So this presence of some of the HKL values will immediately tell you whether it is a BCC or a FCC crystal. So how do we measure it? So I'll just briefly mention this without going into the much detail of it. So you have basically a something known as a X-ray diffractometer. Okay, so this is a instrument which will be used to measure this X-ray diffraction pattern. So you want to generate a X-ray diffraction pattern which you can analyze, so that you can get some idea about what is the crystal structure, what are the lattice parameter, and so on. So what is typically here done is you have to mount a X-ray source. Okay, so you have a source that is more or less, you get monochromatic beam. So you try to make some filters and so on, so that you get a monochromatic beam, so which is incident at angle theta on a sample. This is your sample, and then you detect the diffracted beam on a detector. So this is where you mount the detector. So that means the detector makes an angle 2 theta when you measure or look at it with respect to the sample. Okay, so this is important. So if your x-ray is making an angle theta, so you have to align so that your detector will be always at 2 theta. So this is normally done by your mechanical motions nowadays, which are coupled between. So the sample, if it moves by an angle theta, so detector will automatically move by angle 2 theta. And then you count like how many what is the intensity of the electromagnetic radiation. So if you do that, if you perform this kind of experiment, so typically you will get a result something like this. So you have a diffraction angle 2 theta versus intensity. Okay, so this is the what you observe in your detector. So what you can see at certain 2 theta values, so you have a very intense peak. So this is a X-ray diffraction pattern that is produced from a lead sample. So what you see, this 111, 200, 220, 311. So what you can, if you go back to this table now, you can immediately see that this represents a FCC lattice. Okay, so it is an FCC lattice. Now, so different lattice, different Miller indices, they have different intensity. That is, will not go into that detail. But what preliminary analysis you can do, you know what is the 2 theta position, what is the HKL value. So you can calculate what is the D, the interplanar distance, D. So that you can calculate from the Bragg's law. So this 2D HKL sine theta we can get, because we know lambda and we know sine theta. So theta, you will calculate, this is 2 theta value, so you divide by 2, so you know what is theta. So D can be easily obtained because lambda is known. And this N, so what you observe is the first order diffraction. So this is 111. Okay, so if you look at this 222, for example, so this represents your second order diffraction peak. So similarly, this is the 200, which is the first order diffraction peak. The second order diffraction peak is 400. So similarly, you have also, yeah, so I think this much you can see. So you have to go to much higher angle to see the diffraction peak from this 220. Now, from how we can obtain the lattice parameter from this? So this is a relation or a formula that you use. So once you know D, you know HKL, so you can easily find this A. So this is the relation for a cubic crystal. So this is the relation between D and A. Okay. So you can then find out what is the value of the lattice parameter. So this is how typically you will be doing that. So you will write down what is 1 1. So here 111 should be there, 111 200. So you write down what is the HKL value, what is the 2 theta, you calculate D, and then you calculate A, and you get almost similar from all this. So that is what you expect, because it is a cubic crystal FCC. So you expect that A value should be the same, about zero point 0.5 nanometer. So this is a very useful technique. That's why very useful technique to characterize your material, and you can find out its crystal structure, lattice parameter, and so on. Uh, okay, any questions so far? So this we will not go into the detail of the analysis here, because this will it's not part of the course, but you should be aware of this tool because it is very useful in material characterization. Okay, so the next topic that we are going to discuss is what we call as imperfections in solid, or defects basically. So when you so far that we have discussed, we said these are all crystals which are perfect in nature, but nothing is perfect in nature. So there is no ideal solid that exists. So that means there will be always some defects or imperfections in a solid. So what do we mean by that? So there are basically three types of defect that is normally encountered. So one is called as a point defect. Then the second one is line or linear defect. So also the name is dislocation. Then there is also a boundary or interfacial defect. So which like we saw like a grain boundary. So each defect, so as we as I said, so there is no perfect crystal, so you will always have some kind of degree of imperfection, some kind of defect in any solid that we have. So the best uh, that we can obtain is like perfection that we can achieve is that has been achieved is like 99 point. So after decimal 999949, so that much, so 99.9999% perfection has been achieved, but never 100%. Okay, so we will go one by one about this defect, the type of defect. So the point defect is something like, as a name suggests, so only some point is missing. Okay, so what are those points? So like, let's say this is my atoms that is arranged in a periodic manner. Now, one of the atoms is missing. Okay, so this is possible because of some random thermal motion or something, some energy, extra energy is there. It is possible. Okay, so there will be some processing issues. So this one atom is missing here, so that is what we call as a vacancy. Okay, so these are again names which that is exist in English literature. So there is not a really scientific name. So but as a vacancy means, so there is a absence of an atom there. Okay, so it is vacant. So this is a point defect. So similarly, you can also now, if this is a vacant this atom, let's say suppose there was an atom here and somehow this atom got displaced and you created a vacancy, but where this atom can go to, so it can go to like one of the in between places, so you have still some space here, so it will just squeeze into that. Okay, so it will try to just get squeezed into this whatever space is available. So what you call this kind of defect is a self interstitial. So the name is a interstitial. So this is a self interstitial because the same atom is occupying this interstitial site. So the same atom means it is has the same radius, atomic radius as the original atom. So it tries to squeeze here. Okay, so it is normally not possible, difficult, because if it is equal size, so the chances are low, or the probability is low that one atom can have a self interstitial, but this is possible still. Okay, so how these point defects are created? So this is very interesting. So this is all due to thermodynamics. Okay, so this is this. That's why the name also sometimes these point defects are called a thermodynamic defects. So this relation tells you how many defects will be there per unit volume for a given solid at a given temperature. Okay, so this NV stands for number of vacancy per unit volume. Okay, so that means this is number of vacancy or number of atoms per unit volume. So which can be, unit volume means cubic centimeter or cubic meter. So this N is total number of atoms that you have in the solid. So how many atoms you will have per solid. So which you can actually calculate if you know what is the density of the material. So this also you can calculate if you know what is the crystal structure. Okay. So this is these are all related. Okay. So you, from the X-ray diffraction, for example, you can calculate what is the density. Uh, you can also calculate theoretically if you know what is the crystal structure, because let's say from XRD you know what is the crystal structure. From that you know, okay, what should be the number of atoms per unit per my unit cell, and then you know what is the volume, and from that you can calculate how many unit cells will be there, and from there you can calculate, that means how many atoms will be there per unit volume. So So this n can be calculated from X-ray diffraction pattern as well. Once you know n, and you need to know at a particular temperature this QV. So QV is called as a activation energy to create a vacancy. Okay, so you need a certain amount of energy to knock out one of the atom from its position, and that energy will be typically of the order of, let's say, few milli electron volt, okay, or in joule, for example. So either, so this energy you can write in electron volt or joule. So you need certain amount of energy to knock out this atom from its position. So this, how much energy you will need to knock out, so this depends again on the bond strength. Okay, so how strong is the bond? So if you are at a particular temperature, so this temperature can provide a thermal motion or a thermal energy. So that thermal energy is normally, you write it as K into T. So K here is the Boltzmann constant. So T is the temperature. Now you can give the thermal energy, and if this thermal energy is enough or more than the activation energy, or it can overcome this QV, then you create a vacancy. So this is an exponential dependence, as you can see. So that means if I increase QV, so if my activation energy increases, so this number of vacancy will decrease. Similarly, if I increase the temperature, so number of vacancy will increase, because I am increasing the thermal energy, so I'll be able to vibrate these atoms rapidly, and it is possible that I can break some of those bonds. So that's why this number of vacancy will increase if I increase the temperature. Okay, so you can imagine if you go close to the melting temperature of the material, for example, so you'll be having like almost the number of vacancy will be, so this NV, this factor will be of the order 10 to the power minus 4. So that means you will be having a vacancy of the order of one atom in 10,000 atoms. So if I have 10,000 atoms, there will be one vacancy. But if I am at room temperature, so I'll be having a vacancy, this concentration will be of the order of, maybe you'll have one vacancy in 10 to the power 20, or 10 to the power 15, 16 atoms, and in that maybe one vacancy. Okay, so the number of vacancy will be less. Uh, so this schematic figure basically tells you how this process happens. So this is what the process is captured in a mathematical expression. So what actually happens? So you have, let's say, a perfect crystal. So because of this atomic vibration and motion, so it is possible that one of the atoms will break the bond, and typically it will happen most likely on the top of the material, which is on the surface, because those surface atoms are weakly bonded. Okay, so surface atoms have incomplete bond, so they are bonded. So if I take an atom here within the crystal, so it is bonded perfectly on all sides. But if I look at a surface atom, it is only bonded, let's say, or let's say I take this one, so it will be bonded to this one, it will be bond to this one and this one, but there is no bond on this side. So that means the it is not satisfying all the all, let's say, if it is has to share the electron or exchange electron, it is not happening completely. So therefore the high chance is that you will break a bond easily on the surface. So once you do that, so for example, this atom has moved or displaced to this position, and you have created a vacancy. Now this position can be occupied by a neighboring atom, so this atom will jump here, and the vacancy will move into the crystal. So this is how you will have this point defect or vacancy that will propagate into the, or diffuse into the crystal. Okay, so into the bulk of the material. So this is a nice schematic representation how this vacancy is created. So what this point defect or vacancy will do, so it will change the lattice or distort the lattice. Okay, so because now you have a free space, so there will be some rearrangement of the atoms around the vacancy, so it will distort the lattice around. So sometimes this defect or this point defect can be introduced deliberately. Okay. So what we call that process as a doping or a substitution. So you can really deliberately add a foreign impurity atom into a crystal, and you call it a doping or a substitution, and then you can rearrange the change the lattice, and locally you can change, and that is going to affect also the its physical properties as well. So for example, it can enhance or maybe reduce. So most of the time you add because you want to enhance the mechanical, electrical, or optical properties. So a very good example of this process, this electrical process, is like when we do doping in semiconductors. So in semiconductors, we add, for example, if I have silicon, I will add a boron, which is a impurity atom, and if I do that, so I will make it a p-type material. So this is what we are doing, adding defect or impurity deliberately. So similarly, if I take silicon and add phosphorus, for example, so I will make it a n-type material. And now you know, if you have p and n-type, so you can put them together, make junction, make a device, p-n junction, a diode, you can make transistors, and so on. So doping is also very useful in that sense. So you modify the electrical conductivity, you change the type of charge carrier. So in the n type you have electron as a charge carrier, in p type you have holes as a charge carrier. So this is very useful. So there are different types of vacancies. So one, as I said, you just replace one of the atoms, so that is a vacancy. So we can use a substitution. Okay, so you add a foreign atom or an impurity atom which is larger in size. So if you do that, so what it does, it will distort the lattice, but it is just like pushing everybody away. So you can imagine like a person who is really heavily built. So that person enters into a crowded region, so he'll make more space because he needs more space to be to stay there. Okay. So similarly, you can also have a substitution of a smaller atom. So this is a bigger atom, here is a substitution of a smaller atom. So when we are talking about substitution, that means we are replacing one of the original atom here by this impurity atom. So if I have, let's say, silicon here, so this silicon, one of the silicon atom will be replaced by a boron or a phosphorus. So this is what the substitution we are talking about. So this size of the atom which is replacing that could be larger or smaller. Another possibility of this point defect is this interstitial substitution. So interstitial means, so we have some space in between these big atoms. Okay, so we have, let's say, these big atoms, there is some space here available. So I can put a smaller atom normally within this. So that is also definitely going to change the structure. It is going to change then also the properties as well. Okay. So this is an interstitial substitution. So here in the interstitial substitution, you are not replacing any parent atom. So they are all there, but only thing you are introducing it into the space that is available. So most of the time, this interstitial substitution will even not change the crystal structure at all. So it will change maybe be the lattice parameter, but if it is a FCC, it will remain still FCC. So here we'll give an example. So when you do this substitution, this kind of substitution, impurity, we are adding impurity. So whether it is a substitution or a interstitial substitution, so what we form something known as a solid solution. Okay, so solid solution, like we have liquid solution, like you add two different liquids, you mix them, so you get a perfect solution. Okay, so that is that happens in liquid state. The same thing also happens in solid as well. So that's why we are calling it a solid solution. So you add a foreign atom and it just goes into this parent uh, solvent, so to say, and it occupies some position there and it becomes part of that solid. So you have a solid solution. And by doing that, so you don't change the crystal structure, as I mentioned. Okay, so when we talk about the substitutional uh, solid solutions or impurity, when you add a substitutional impurity, so which type of atom you can add, so is governed by a rule known as a Hume-Rothery rule. Okay, so this is a very famous rule which tells you whether you can add a particular impurity atom to another uh, solid or not. So what are those rules? So there are four rules. So first you have to look at what is the atomic size. So when you want to add any foreign atom, so you have to see what is the atomic size. So you cannot just add any random any atom to any solid. So the atomic radii, the difference in the atomic radii should be of the order of plus minus 15%. Okay. So whatever, let's say if the parent atom has an atom with atomic radius, let's say uh, x. So now the atom or impurity atom that you can add, so which will create a substitution, which can substitute means it can replace this parent atom and occupy that. So the atomic radius, the the tolerance is about plus minus 15%. So if it is more than that, so you will not get a substitution. So it will be probably there, but it will form a different phase, so it will not go in form a solution, solid solution. uh, if you add a bigger atom or even a much smaller atom, so it could create a new phase. So if I have, for example, as I said, so the substitution does not change the phase. If it is FCC, it will remain FCC. If it is BCC, it will remain BCC. But if you add a higher an atom, impurity atom which has high atomic radius, so it can create a different phase. The second point is the crystal structure. So ideally what you want, and most likely the solid solution will happen only if both the atoms have the same crystal structure. So same means it should be FCC or a BCC. So not it is not like a cubic. Okay. So the crystal structure, either it should be FCC, both should be FCC, or both should be BCC, or both should be a hexagonal HCP or so. Another third point is the electronegativity. So this electronegativity, the difference in the electronegativity should be small. Okay. Uh, so if I am adding two atoms where the electronegativity is, the difference between the electronegativity is much larger, so it is also will not form a substitutional solid solution, but what it will form is known as a intermetallic compound. So it is called as an intermetallic compound. So this is a class of material. So it is uh, people deliberately also make intermetallics as well for certain applications. But normally, if you want to have a substitution, so you want to avoid that there should not be a big difference in the electronegativity. Then the final point of the rule is that the valency should be same, or like the atom which you want to substitute, so its valency should be should be higher. Okay. So I'll show you the example. So if I am adding an atom B into atom A, and I know what is the valency of both atoms, so the valency of B atom, which I am substituting, should be the same as the valency of A, or should be more than the valency of A. So if it is less, again it will form the intermetallic or other phase. So here is an example of this. So this copper and nickel, okay, a very good example. So nickel, you can completely really dissolve it. It's like really you can make it soluble completely in copper. So there is no distinction. Although copper and nickel, they are completely different atoms. But when you form a solid solution, this nickel goes easily substitute the copper atoms. So why? So if you now apply those four rules, So what you see, if you compare, let's say, the atomic radii, so copper has 0.128 nanometers, nickel has 0.125 nanometers. So very close. So not a big difference, even it is less than 5%. The crystal structure, both are same, FCC, FCC. That is good. Electronegativity, very similar, 1.8, 1.9. The valence, normally copper has plus 1, so sometimes it can have plus 2, but mostly it is plus 1. And then nickel has a plus 2 valency. So then nickel can easily, therefore, substitute copper. So they form a really good solid solution. Okay, so the next type of solid solution is related to the interstitial defects that we discussed. So interstitial now means, so we are adding a foreign atom which goes or occupies a space in between the atoms, the parent atom. So it is not replacing the parent atom, but it is, the parent atoms will remain there as many as they were, but it will just go into the space that is available around those parent atoms. So that means this interstitial substitution will always have a smaller atomic radii or ionic radii compared to your parent atom. So in general, so there are two such interstitial position that an atom can occupy. So one is called a octahedral, the other one is called a tetrahedral. Okay, so you have two possible sites. So octahedral site and tetrahedral site. So the site, the position where this atom can go also is quite well defined. So it cannot go to any position. So, for example, if you look at a this is a FCC crystal, for example. So if you look at a FCC, so the octahedral position can be 0, half, 1, or half, half, half. So that means if you go along the body diagonal by half a unit cell, so you will reach this point, which is your octahedral site. So similarly, if you go along the edge, one of the edge by half, so you will also get an octahedral site. So this is where the one of those atom can go, and the size is definitely smaller than the parent atom size. So there is also a possibility that tetrahedral position is there. So where it goes to this particular coordinate. So 1/4, 3/4, and 1/4. So which you can now calculate by assuming where the origin is. So we saw earlier like how you can index a point or find out the coordinate of a point. So you move 1/4 along A axis, 3/4 along B axis, and 1/4 along C axis. That's way you will get a tetrahedral. If I take BCC, for example, so the coordinates for a tetrahedral and octahedral changes. So in this case, the octahedral sites are either, so along the edge it is still there, so one of the edge, and the octahedral site can also be one of the face. Okay. Similarly, tetrahedral will be given by the coordinate 1, half, and 1/4. So these are all fixed, decided. Okay, so you cannot really change the position of this tetrahedral and octahedral sites. You may do a little bit of distortion by introducing that, but these positions will be quite fixed in a unit cell. So how do we know which is a octahedral and a tetrahedral? So it is normally known from its coordination number. So coordination number means with how many atoms, what are the next nearest neighbor of these atoms. So this is an octahedral coordinated atom or ion. So it is, if it is coordinated with 6, 1, 2, 3, 4, 5, 6 next nearest neighbors, so it will be called as a octahedral. So that is why the name octa. Okay. So if it is a tetrahedral, so 4, so it is bonded to 1, 2, 3, 4. Okay, so this is a tetrahedral atom. So now if I look at, go to this FCC for example, and I say this is my octahedral position, that means it should have six next nearest neighbors. So what are those six? So you can immediately see this face centered. There are one, two, so this is a face centered, three, four, and five, six. So these are the six next nearest neighbors for this octahedral site. So similarly, if I go here, so this also will have six coordination. This one, this one, this one, and then I'll put another unit cell nearby. So on the, if you add another unit cell to the front here, so along this axis, so you'll have one atom here. So similarly, there will be one atom below here and one atom above here. So there will be another unit cell here, so another face center. So this will form the six coordinates. So if I look at the tetrahedral, so it will be bonded to four. So what are those fours? So it will be uh, yeah, one, two, three, and four. Okay, so two of the face center and two of this edges, corners. Okay, so this will form the tetrahedral set. So similarly, you will also see here also it will have six coordination, as well as this one, the yellow one, will have four coordination. So this interstitial substitution is a very famous example, is the carbon that you introduce in iron. Okay, so this is a interstitial substitution, and you can put add carbon up to only 2%. So if you add more than 2%, so what happens? So it will form a separate phase. Okay, and why it is possible? So the carbon has a very small atomic radii, so it is of the order of 0.07 or something, compared to iron. Iron will be having twice the atomic radii, so it is of the order of 1.14 or 15 nanometer. Okay, so whereas carbon, the atomic radius is of the order of 0.07. So because it is smaller, so it can now occupy the interstitial site. So this interstitial substitution happens quite a lot in many ceramic material. So if we have some time later on, I will show, when we talk about some examples of or other properties, we will discuss about that in detail. Okay, so the next kind of defect is called as a line defect or dislocation. So this is, so one, there are several kinds. So one is called a edge dislocation. So edge dislocation, as you can see here, so we have this is a one-dimensional defect. Okay, so this is a line defect or a linear defect. That means a line defect. So that was a point defect. This is a line defect. So as you can see here, so you have these set of atoms, so which are arranged quite regularly. But as you can go down here, so this one particular atom, the column is completely missing. So from all these columns are missing. So that what it causes, so it causes a distortion. Now a line, this line exists up to here, but after this there is no such line. So that means, so these atoms will now come closer together. Okay, so this will have a distortion here, and normally, so the edge dislocation starts from here, and which is given by this line, and normally represented by this symbol. So this reverse T represents that symbol. And the, now due to this dislocation or new set of atomic planes that is introduced here, so this changes the lattice parameter. So this change is given by this vector, which is called as a Burger vector B. Okay, so this is a very when this vector is important, particularly when one wants to study about dislocation. So you will see the symbol. Normally the symbol will be used so to represent there is a dislocation, edge dislocation, and this vector will represent, quantify, like how much is this burgers. So this is a burgers vector, that is the name it is used for analysis. Then there is another type which is known as a screw dislocation. So this is a different type of dislocation. It is formed due to a deformation. Okay, so it is like a twisting of like one block over the other. So you could see like you have two blocks. Okay, so one block is kind of rotated or deformed over the other, uh, the bottom part, and that leads to a form of a line defect. So now you create an extra line of atoms, which is not present, and that you identify or you call as a screw dislocation. So screw, because now you are getting a spiral kind of movement or deformation, so that is why you are calling it a screw dislocation. So this will be again identified with a this Burger's vector B. Okay, so each dislocation will be assigned to a Burger's vector. So this will be like this distance, because you have introduced this extra uh, atomic plane or line. So this atomic distance will represent this Burger's vector. So sometimes also what you get is like a mixture of this. So most of the cases when you look at dislocation, so dislocation will be a mixture of both. So you'll have a edge dislocation as well as a screw dislocation. They will many times will exist together. Okay, so it is not like you will be either having the line or only screw, but most of the cases both will exist together. So this dislocation is sometimes useful. I mean, necessarily it is not a good thing to have, because they degrade their mechanical properties of the material, particularly when you look at the strength of the material, uh, uh, like how much they can resist to a deformation. So if you have a dislocation, so it will easily break. Okay, so because already you have a line defect there. So if you are applying certain kind of force, so it will break along that dislocation line. Okay, so that's why these dislocations are undesirable, and what you want during the processing when you are fabricating or synthesizing your material, you try to avoid this dislocation. Okay, so this is like just wanted to show, this is a microscopic electron microscope image to show how this is a titanium based alloy, a commercial alloy, where you could see these black lines. Okay, so there are plenty of these black lines. So these all represent the dislocations. So because of the poor processing, you have lots of dislocation in this sample. Okay, and they are definitely going to affect the the mechanical properties of this alloy. So mechanical strength, the Young's modulus, so all these will change because of this dislocation. And why do they arise? uh, Normally they will arise due to something known as a mechanical deformation or a plastic deformation. So that means a plastic deformation we'll discuss a little bit later. So uh, what it means, like a plastic deformation means you are applying a force, okay, a deforming force or a stress, and you are measuring the strength. Okay, now that curve, so whatever you apply a force and you measure this change in its dimension, okay, so that you plot, and that what you call as a plastic deformation. And due to, like, if you apply too much stress, so eventually there will be a formation of dislocation in the crystal. So this will so people then perform this kind of experiment, so that you know what is the maximum strength you can apply to a particular alloy or a particular material. Okay, so this is a typical experiment people do. So this dislocation can also arise during a solidification process. So when you are making this material, so the making of material, we are doing it by cooling down from a vapor, condensing it from a vapor, or a liquid phase. So when you are doing that, so in the process, so a dislocation can also, so defect will be also there, and this point defects, and this dislocation can also happen. So sometimes it also happens due to the thermal stress. So thermal stress means if a material is operating in a high temperature condition, okay, so where it experiences a lot of high temperature, so where for example it is used in aerospace, or it is used in machines which are working continuously for several hours, so there will be a lot of temperature will generate, okay. So in those conditions there will be thermal stress, and that stress will lead to certain kind of deformation, and this dislocations will also occur. So your goal is, that means if you want to avoid, so once these dislocations appear, so the strength will decrease. So you want to know what are the limits up to which a material can withstand a stress. It could be a thermal stress, it could be a mechanical stress, or it could be any other stress. Okay, so the third kind of defect is a boundary or an interfacial defect. Okay, uh, so this is, again, you could say it is I mean, it is a two-dimensional defect. Let's say, so we saw the vacancy, which is a zero-dimensional defect. The line defect or the dislocation is a one-dimensional defect, and then the third type, which is a two-dimensional defect. Okay, so this is what we call as a boundary or interfacial defect. So the first, this interfacial or defect will be due to the external surface of a material. Okay, so if I take any material, so there is always a surface. Okay, so that surface, there are atoms definitely on the surface. Now those atoms, they, as I said earlier, so they have an incomplete bond, because so the atoms which are within the material, so they are, let's say, if they have six number of coordinates, or next nearest neighbor, they will find those nearest neighbor. But the atoms which are on the surface, so they will have half of those neighbors, so other neighbors will be missing because there is no more atom, no more material there. So that means those atoms are highly in an energetic state, so because of this incomplete bond. So you can have a lot of adsorption of other molecules and so on the external surface of a material. So you have adsorption of water vapor, or maybe some other oxygen or hydroxyl ions, or any other entities that is there in the atmosphere. They can get adsorbed because that is what, there is too much energy there, incomplete bond is there. Now this is not an issue in liquid. Okay, so if I take a liquid, so this, there exists an external surface, there will be incomplete bond. So but what they do, because they are flexible, so they can change their shape, and they can minimize this surface atoms. For example, if I take a water droplet, so if a free droplet will take the shape of a sphere, so that way it will minimize its surface energy. Okay, so that is the best shape to minimize the surface energy. So it will acquire the shape of a sphere. But in solid, it is not possible. So they are not that flexible. It is not possible. So you will be, uh, you have to stay with the surface atoms, which will create a high energetic state, and uh, they will, so they can be useful, for example, in catalysis and so on. Then the second type is the grain boundary. So grain boundary we already discussed, because you have a polycrystalline material. Now different regions. So this one grain meets another grain, for example. So we have three grains here. So one, two, and three. So now these two grains, they meet at this, and they have completely different orientation of the atomic planes, and that is what you get this high energetic state, the grain boundary. So when you look at this grain boundary, so they can have a very high angle or a low angle. So this angle you can measure. So like a line is drawn, and then you see how much the atomic planes deviate from one grain to the other grain. So this deviation will decide what is the angle of this misalignment, or if it is high, so you will call it a high angle grain boundary. So this boundary will be a high angle grain boundary, and this boundary will be a low angle. So again, you draw a straight line which connects, let's say, the same atoms which are oriented same way, and then you see how much is the deviation from this particular orientation between these two grains. And here this angle is quite small, so compared to this angle, so this boundary will be called as a small angle grain boundary. So these type of grain boundary will exist in, these are all is a two-dimensional or interfacial defect. So this interfacial, when we talk about interfacial, means you have two different interfaces. So the interfacial comes from the term interface. So you have two different types of material, they or two different, any two different things when they meet, so we form a interface. Okay, so that is what this means. Then another kind of a boundary is called a phase boundary. So what is a phase boundary? So phase boundary will look similar to a grain boundary. Okay, it is a kind of a grain boundary, but you have two different phases here. Okay, so here what we have, you have the same phase. So phase means if I have a crystal structure of FCC, both will be FCC here, or both may be the similar same matter. So that is will be the a typical normal grain boundary. But if I have a phase boundary, so I will have two different phases. Okay, so this can be different. This is one kind of atom, this can be a different kind of atom. So when they meet, so they will form a boundary which we call as a phase boundary. This is also a kind of a interfacial defect. So why they will be there? Now if you go back, so when we talked about this carbon in iron, for example, so if I make an alloy like this, when I add carbon to iron more than 2%, so what will happen? So iron carbon up to 2%, you will form a solid solution. But if I add more carbon, so this carbon will precipitate and form its own phase. So it could be in a graphitic phase or in a diamond-like phase. So most often it is in a graphitic phase. So you will see that means now you have two phases. So if I am adding, let's say this is iron, I am adding carbon, so up to 2%, so you will have an interstitial. But then if I have more than 2%, so this carbon will segregate and form its own phase. And then you have a phase boundary between them. So you have a grain boundary between a carbon which is segregated and another which has 2% of carbon in iron. So they will form a boundary which will be a phase boundary. Another interesting boundary is called as a twin boundary. So what is a twin boundary? So this represents this twin boundary. So it is, let's say I have a set of plane here, so something like this. Now I create now at this boundary, now the orientation, the HKL orientation changes. Okay, so this now I have here, let's say atoms A, C, F, B, E, D, like that. Okay, so this is one kind of orientation. Okay, something like this. And here another kind of orientation. Now the boundary here, if I draw a boundary along this line, so it exactly looks like a mirror. So that means if I look at the atoms on both sides of this plane, so this is a two-dimensional thing. So if I look at atoms on both sides, so they will be just mirror image of each other. So for example, A prime is a mirror image of A. So C prime is a mirror image of C. B prime is a mirror image of B, okay, and so on. F prime is a mirror image of F. E prime is a mirror image of E. D prime is a mirror image of D. So you have a mirror image of the atoms about this boundary. So that is why the name is called as a twin boundary. Okay. So these are the type of boundaries or defects that exist in a solid. I The defects are normally what you want. You want to avoid those defects, but as I said, the defects will be always there because a solid is not a perfect solid or not an ideal solid. So you have to live with those defects. So sometimes you make use of those defects, and those defects will modify or change the structure. They will also change, by changing the structure they will change the properties as well. So we will discuss the effect of some of those properties, how they're affected, this mechanical properties, for example, when we discuss about a plastic deformation. So we'll not do it in the next, so we'll not this class, but in the next class we'll discuss about that. If you have any questions so far, you can ask anything from this defect part. Any question? No? Okay, so one thing I just want to add before moving on to the next topic. This defects is how you can see these defects. Okay, so this is a very important point because we are telling about, okay, this kind of defect exists. So a line defect exists, a grain boundary exists. So are we able to observe those defects, or we are just kind of theorizing this? Is it just a theory? We are describing some mathematical expression for them, and they really exist? So it is possible to see that. So for example, if I take a to see this grain boundary, so you just have to perform a optical microscopy. Okay, so you have to just perform an optical microscopy. You put it under optical microscope, and you can see the grain as well as the grain boundaries. And typically, of course, the grain size or grain size should be of the order of more than a micron, because that is what a optical microscope resolution is. So but if the grain size is like few hundred micron up to few millimeter in many cases, so if you do look at those grains, you will also identify the grain boundaries. And normally, because as I said, the grain boundary has a very energetic atoms, so a lot of vacancies, a lot of open bonds are there. Okay, many impurities will be there. So what you have, like in an optical microscope, what is the process? So you shine it with light, and then light is getting reflected, and I will see the reflected light. But if there are too many defects and vacancies and incomplete bonds are there, so the scattering will be too high from the boundary. If the scattering is too high, so they will all diffuse and go into all directions, so you will not get a perfect reflection from there. So if you don't get a perfect reflection, so that part will appear very dark in your microscope, and that is how you can easily identify that this is a grain boundary. So that is how even people count, like how many grains are there, how many grain boundaries are there. So you can even do a quantitative analysis just by taking a image with an optical microscope. Okay, so now if you want to see dislocation, for example, so you cannot use this optical microscope anymore. So you need to use an electron microscope. Okay, so electron microscope, like I gave an example of that just here. So here this is a micro electron microscope ACM image. Okay, So you will see with a scanning electron microscope, and again you see these dark lines. That means the electrons are getting really highly scattered from those regions because they are all energetic, and uh, they interact strongly with the electrons. So they again appear dark compared to your white contrast that you get from the sample. Now, to see the point defect is not that easy. It is possible. So you have to go to something known as a transmission electron microscopy. So where the resolution will be much higher. So you can magnify like 100,000 times, a million times you can magnify. Okay. So when I talk about optical microscope, so the magnification is you can go up to 1,000 or maybe 10,000 times magnification. In an electron microscope, you can magnify 100,000 or like a million times magnification you can do, and in that case even you can see individual atoms. Okay, so that way you can actually look if the one atom is missing. So similarly there is another technique which is called as a scanning tunneling microscope, STM. So in that also people observe, do this, look at atoms, position of atoms. So people have observed the vacancy in silicon, for example. So you take a perfect silicon crystal and you look at with a scanning tunneling microscope, and people have observed this atoms missing, silicon atoms really missing from that position. So these are all possible, and one can see or observe experimentally also these defects. And once you do that, so then you can correlate with your properties that you have measured. So once you have identified, okay, this kind of defects exist, then you can correlate with whatever properties you have observed or measured. Okay. Okay, so any no question? If not, so we'll now move to the other part. The We are now what we have discussed. Like we started our discussion with what is the structure. So what is the bonding? What is the structure in an atomic scale? And then we talked about like what are the kind of the imperfections or defects that can have in a solid. So now we are moving into a topic which is related to, so this is called diffusion, which is related to how these atoms move in. So we talked about solid solution. So we said one atom enters, substitutes, and occupies one position. So how this happens? Okay, so this is what we call as a diffusion process. So all this is related to a diffusion. Diffusion means a process in which we are transferring some mass. So in this case the atoms, so we are transferring the atoms from one end to another end, or one place to another place. Okay, so over certain distance, so these atoms really physically they are moving, right? So and this movement what we call as a diffusion process. So this diffusion is quite common. So in gas, for example, so if I take I mean I have a room and uh, uh, so I burn like a agarbatti. Okay, agar agarbatti, if you put it there, so you have the smoke that comes from that one end and it will spread everywhere. And how this happens? So those molecules now they are diffusing through this gaseous medium from one corner and they spread to all part. Okay, so this is the diffusion process. This is quite common. It will happen in gaseous medium. It also happens in a liquid medium. Okay, so diffusion, it you can call it in different form, but it will be a diffusion process. Because let's say when I'm boiling water, for example, so I'm boiling now the water molecule on the bottom, so when they get highly energetic because they get heated up, so they will move to the top part, and then there will be the water molecule which on the top which are colder, so they will move down. Okay, so this is again a diffusion process. uh, so in fact, if I take a hot water and cold water on two sides, okay, and now I open and I want to mix, so there will be a diffusion of hot water molecule, the water molecule from hotter side to the cooler side. Similarly, there will be a diffusion of water molecules from cooler side to the hotter side as well. So there will be diffusion of water molecule. So the same thing is also happening in solid as well. So this concept or the idea can be understood from this figure here. So this figure, this kind of figure is called as a diffusion couple. Okay, so we are calling it a diffusion couple. So what it means? So here an example of again a copper and nickel has been taken. So we take one copper and one piece of nickel, and we just put them together. So we have created an interface. So they are just like that. Okay. So if you look at the atomic arrangement, so it will be like here only copper, you have here only nickel. Okay. So the blue one is nickel and red one is the copper. And if you look at the concentration, so this is the concentration in the y-axis and the position. So you have concentration copper 100%, then a 0. So it's a step. Similarly for nickel, you have 0 nickel here, a step, and 100% nickel on this side. Okay, so that is expected. And this is what you have situation when you put these two copper and nickel together. So that is the room temperature. Now, if you do a high temperature, these two interface, now both the material you put it at a high temperature means about 1000 degrees Celsius, let's say. Okay. So if you do that, so what you will observe that these copper atoms now they will diffuse into nickel. Okay, so to the right, nickel atoms will diffuse or move to the left. So why it happens? Because there is a difference or the difference in the concentration. Okay, so you are of course giving a thermal energy. Okay, a thermal drift, but you have a concentration difference. So copper, there was no copper earlier here, so there is maximum concentration here, zero concentration of copper here. So that means there is a tendency for copper to move towards right. So similarly there is a tendency for nickel to move towards left. And in the process, so what you will get is a copper and nickel alloy. So what you see here now, that some of the blue has moved into the red region, and some of the red copper atom they have moved into the nickel blue region. So if you now look at the concentration, so it is still, let's say, 100%, but you see a change in concentration. There is a increase in concentration of copper in the nickel, and similarly there is a increase of concentration of nickel in the copper region. Okay, so this is what we call as a diffusion process. So this is normally the term is used interdiffusion or impurity diffusion. So this is one kind of diffusion. So there is also something known as a self diffusion. Okay, so self diffusion means if I have taken only one kind of molecule or an atom, so there will be diffusion of that atom. But why it will happen? So it will happen if there is a difference in the composition. So we'll discuss maybe later on. So this composition is an interesting aspect, but this self diffusion can also happen. So if there is a composition gradient, okay, so here we have a concentration gradient. So copper is maximum on left side, zero on the right side. So there is a concentration gradient. So that drives the copper to the right hand side, so that it gets equilibrium. Okay, uh, so of course you have to give certain energy, so that is a thermal process. So this is not going to happen at room temperature, so you have to give thermal energy, so temperature. So what is the mechanism of this diffusion? So there are two processes basically. So it is again related to the defects that we discussed earlier. So diffusion happens with the formation of defect, movement of defect. Uh, so diffusion is always associated with that. So that's why we need this high temperature, so that we can create enough amount of vacancy or defect, and then we can move these atoms from one place to another place. So as we discussed about the defect, so the diffusion process, the mechanism is also associated with that. So one is called the vacancy diffusion or vacancy associated or mediated diffusion. Then there is also interstitial mediated diffusion. So again comes from the same uh, defect that we discussed earlier. So if I now take a crystal, so I have uh, a atom which is a substituted atom. So this is another atom which is replaced. So atom B has replaced atom A. Okay. And now if I have created a vacancy, so this atom B will move to this. Okay. And that is how it will diffuse. So the vacancy also moves or diffuses, and the substituted atom also diffuses. So either it can diffuse in any direction depending on where the vacancy is created. So in this diffusion process, a vacancy moves here and the atom B moves here. So now probably this atom can move to another. So a vacancy will be created nearby. So then this atom can move or diffuse. Okay, so this is how it will move into, let's say, for example, this copper will diffuse into the nickel side. So there will be somewhere a nickel vacancy will be created, and the copper atom will occupy that vacancy, and slowly it will move. So you can imagine also this is a slow process. Okay, so it is not really a fast. It will not happen like quickly within seconds. So position the interstitial diffusion example is like I have an interstitial uh, atom, so the smaller atom, so it is a interstitial site and the atom occupies that. So now there can be another interstitial site, and this atom can move easily there. Okay, so we, as we discussed, it will be a tetrahedral, octahedral. So the atom can go from octahedral to tetrahedral, or a tetrahedral to octahedral, or maybe uh, tetrahedral to tetrahedral, or octahedral to octahedral. That is possible. Okay, so this is now this atom, this interstitial atom now is getting diffused into the solid. So again, it will happen due to a temperature or a concentration gradient. Okay. So how do we understand it uh, the mechanism in a form which we can then write down and solve it? Okay, so this is again a mathematical representation of this diffusion idea. So how we can put it in form of some equations. So if you look at a diffusion, so it is basically it is a function of the concentration gradient. Okay, so this is what we call as the driving force. So the driving force is like what is the tendency or why the atom will diffuse, because there is no concentration of that atom. So they say agarbatti jalaya. So now we know the those atoms they will move because of the concentration gradient. Okay, so this is what is being represented in a simpler way in this picture. So here we have taken a thin metal plate. Okay, and we have a gas molecule, gas which is at a pressure Pa on the left hand side, and we have probably gas at a pressure Pb on the this side. Now the pressure is much higher on A side and compared to the B side. So that means we have more pressure on this side and less pressure on this side. So that means there is a tendency, there is a concentration gradient. Okay, so pressure more means I have more number of uh, gas molecules on this side. So they will try to now diffuse through this thin metal plate so that they can come across and occupy this side, B side. Okay, so this is the driving force here. So there will be a diffusion through the thin metal plate. So here we can then define few terms. So what we call as a flux. So flux means how many of those atoms are getting the moving across this cross section. So this we have certain area of the plate. So how many atoms or how much mass is moving across this area per time. So that is the flux. So this is why we are defining this m. So the mass of the atom, atomic mass or the molecular mass divided by the area of this thin plate divided by the time. Okay, so this will be the flux. So uh, this is again a typical term that is used when we discuss about a flow of something. So when we talk about flow of water, so there also we talk about what is the flux. Okay, so that means how much water volume of water is moving across a cross section over a time. Uh, so before going into actual thing, so what one can uh, think of is like, so we have some amount of gas molecules on the A side which are diffusing through the metal and they are reaching the side B. Now, in this process, what happens? So you will have reach, or this will you will eventually have a situation which we call as a steady state will be achieved. A steady state means that means you have some number of atoms or gas molecules that enter on this side, and the same number of atoms will come out on the side B. Okay, so no atoms will be accumulated or aggregated within the thin metal. So whatever enter into this thin metal, they all will come out. So that is a steady state condition, and that under that condition, so this flux will be, as I said, it is a function, it is proportional to the concentration gradient. So if I take a one dimension, so it is along x direction, so the concentration gradient is given by dc by dx. Okay, so this then the proportionality constant will be given by d. So d is the diffusion coefficient, which is measured normally in this unit meter square per second inverse. Okay, so the negative sign means it is going from a higher concentration to a lower concentration. So that is why you will have a negative sign. So this is known as a Fick's first law. So this is a well-known law that relates your flux of diffusion of any transport of any matter, okay, any mass across a cross section. So if you know what is the diffusion coefficient, so you can calculate the flux if you know the concentration gradient. Okay. So the concentration gradient will be given by this dc by dx, that will be the slope of this curve. Okay, so this slope, so now if I have a steady state, so there will be no change in this slope. Okay, so whatever amount concentration will be there at a time t, so the same concentration uh, will remain in a steady state. It will be always the same here, concentration on A side and concentration on B side. Okay, so these will remain always the same and the slope will not change. So then I can calculate the gradient. So CA minus CB divided by this XA minus XB. So XA and XB will be the position or the width or the thickness of this metal plate, so to say. So I will have this, so I can calculate the concentration gradient, and then I can calculate the flux if I know the diffusion coefficient. So this is there is a very good example of how this is used for purification of hydrogen, for example. So in hydrogen, so what happens, you take a mixture of hydrogen, oxygen, nitrogen, and many, okay, so many such like an impure gas, so to say. And what you want, that you want to filter out only hydrogen. So what normally people do, you put a metal plate, so which is made up of palladium. So palladium is a special material because it allows only a selective diffusion of gas, and that selective gas is hydrogen. So it only allows hydrogen to pass through it. So in that process, so all this oxygen, nitrogen, or carbon, whatever is in the atmosphere or in the environment, so they will stay there. So only hydrogen will diffuse through the palladium plate, and you will collect pure hydrogen gas. So that is how this hydrogen purification happens. So this is only an example of how you can calculate this concentration or the flux. So the problem is like a plate of iron is exposed to a carburizing or carbon rich atmosphere. So you have a lot of carbon on one side of iron plate, and less carbon on the other side at 700 degrees Celsius. So if you have achieved a steady state condition, so calculate the flux of carbon through this plate. So for that, you need to know what is the position or the thickness of the plate. So that is 5 and 10 millimeters. So this is 5 millimeter thick. And then uh, you need to know what are the concentration. So the concentration are 1.2 and 0.8 kilogram per meter cube. So this is concentration. So per unit volume. Okay. So whatever the mass per unit volume. So that is what we are saying the concentration. And the diffusion coefficient is 3 into 10 to the minus 11 meters square per second. So this number is like really small. Okay. So diffusion is a slow process. So if you want to have a higher diffusion, so this diffusion depends on the temperature, diffusion coefficient. So if you want a fast diffusion, so you normally increase the temperature. So you have all the details, so you can just substitute that and you can calculate what is the G. So by substituting, so where you get, so this is the flux. That means 2.4 into 10 to the power minus 9 kilogram of carbon will be diffusing across this iron. Like this is the area. So if I take 1 square meter of the plate, so per second, 2.4 into 10 to the minus 9 kilogram of carbon will be transported from one end to the other end. So you can now convert it into the number of how many carbon atoms that correspond to, because you know what is the atomic mass. So you know, so 1 mole will be weighing like 12 gram. So you can calculate how many carbon atoms this correspond to. Okay, so most of the cases, actual in reality, what we see is a non-steady state diffusion. Okay, so the steady state is a very ideal situation, which is normally you don't encounter. So what you actually observe is a non-steady state. So that means your concentration or the concentration gradient and diffusion coefficient D may not be constant over time. So it may change. So it is a dynamic now. Okay. So it may change over time. So therefore, this second law was proposed, Fick's second law, so which represents a non-steady state diffusion process. So where you calculate what is the del C, the change in concentration over time, so which is related to the change in concentration, the concentration gradient, and diffusion over the space. Okay, so it correlates the change in concentration over time to the change in concentration with respect to the diffusion coefficient over the space. So when you look at this concentration of diffusing species, okay, and as a function of distance, so earlier what you see is in a steady state, you have this kind of behavior. Okay, so a slope which remains invariant, there will be no change. But in this case, so this will change over position it is changing, and with time it is also changing. Okay, so this concentration of whatever diffusion is process is happening, so it will change over space, over the distance, so to say. It also changes over time. So that means, uh, because now at a particular time, so the diffusion coefficient may be different, the concentration gradient may be different, both are dynamic. Okay, so we will discuss more about this non-steady state in the next class in more detail. And we can see that if I have this, uh, in a diffusion coefficient, in many cases may not really vary as a function of this space or a distance. So so here we are all taking a partial derivative. Okay, so it is a partial derivative, so that means your concentration, so what we are saying, this concentration is a function of the position where you are looking at, and it is also a function of time. So earlier, this concentration, the steady state, so the concentration here is always the same. So it is concentration everywhere, it is the same. Okay. So when we talk about, for example, this situation, it is concentration everywhere, it is the same. So it doesn't vary over position. Only at the interface it is vary. Okay. So and over time again it is constant. But most of the diffusion it is a non-steady process. So that means your concentration will be different when you look at over a period of different time, and also it will change when you measure at different positions. But in many cases this diffusion coefficient may not be uh, really vary too much on the as a function of this position. So you can take it out from this bracket, and what you will get is d will come out. So what you will get is a del square c by del x square. So a double derivative, so double partial derivative of the concentration. So this change in concentration as a function of time will be multiplication of the diffusion coefficient into del square c by del x square. So we will look, give some example how this non-steady state diffusion leads to like particular example we will talk about, because this is quite interesting and very useful for material science. Okay, so I will stop here for today. If you have any question, you can ask. Any question from any of the sections, or any other question if you have? So if you have question, you speak loudly.
Hello, sir.
Yes.
I have a question in Bragg's equation.
Okay.
You have shown a graph intensity versus uh, angle 2 theta.
Yeah.
Yes, sir. What is its physical significance, sir?
What
Diffractal
is
angle.
the angle?
Yes, sir. Yes, sir. 2 theta here. You
Ah,
have
okay. So 2 theta. So if you look at this experiment, okay. So when you're performing an experiment, so you have an X-ray source and you have a sample. So this is your material. So your beam is X-ray beam is incident at angle theta. So now you want to record this interference pattern. Okay. So diffracted, the diffraction, whatever comes out after it is getting scattered from your sample. So this is where you are measuring the intensity using a detector, and you mount the detector at an angle 2 theta. So you have to do that because then only you will satisfy your Bragg's condition. So if you put your, so your angle of incidence is theta here, okay,
okay,
and
sir.
this detector angle is somewhere else. So you will not observe, actually if there is if it is if it satisfies the Bragg's condition, you will not be able to observe that. So you have to maintain this relation theta and 2 theta. So if I draw, let's say for example, यहाँ पे जो dash line है, so you have a dash
Yeah.
line here. So if I extend it like in this direction, so this angle is theta and this angle will be theta.
Yes, sir.
But if I look at what is the angle the detector is making with respect to the incident direction, that angle is 2 theta. So this is just again comes from geometry. So this is just यहाँ पे ये this is one line and this is
Yes,
another
sir.
line. Okay, so I know this angle is theta. I know this angle is theta. So the other angle, like so if you draw it like two lines, so I cannot draw it here, but if you draw it, so you will easily see this angle should be 2 theta. Okay, so that means whenever now in a experiment what you do is, so you let's say there are different ways. So let's say one of the ways you fix the source, and
Yes,
then
sir.
what you do is you scan your sample to change the angle theta. So if you do that, so you have to move the detector to 2 theta, so that you know, okay, my Bragg's condition is satisfied. So as I said, Bragg's condition is not the sufficient condition. So you have to have, like, depending on the material, which HKL value will give the intensity. So that will be decided by whatever, whether it is a FCC or BCC. Now, if Bragg's condition is satisfied and that the reflection rule is satisfied, so you will immediately see a intensity here. That is what happens. So if for this particular sample, so if I put the detector at, let's say this is around 30, this is 35, so this is around 32. Okay, so
Near about
32, between 32 and 33. So if I put the detector at 33, so here the sample has made an angle of 15 degree about, so 15 point something,
yes, sir.
or 16 degree, let's say if it is 32. So it has an angle of 16 degree with respect to the X-rays. Okay, so this angle is 16, and I have to put it at 32 so that I can capture this diffraction. Now, if my detector is at 31 or 33, I will not see this intensity. So that's why this angle is very important. And once I do that, so then again, so that is, so the scan will be typically, so as you change theta, let's say by, so normally you will do it in a step scan, so you change it by a 0.5 degree. Okay, so or 1 degree, so you change, so go from 30 to 30 point, or you start, let's say in this case you have started from almost 2 or 3 degrees, so let's say you start from 10 degree, so you go to 10, 10.5 into theta. So accordingly, so theta will go from 5, 5.025. So if the angle is zero point 0.5 in the 2 theta, so the corresponding angle in theta will be half of that. Okay, so that way you will capture the whole X-ray pattern.
Yes, sir.
Okay.
Yes, sir. When the sample is taken, it is as a plane mirror type system, or we consider the internal atoms, uh, the angle we are taken surface from surface.
Angle, you don't think about what is the internal arrangement. So internal
Yes, sir.
arrangement will come out based on the Bragg's laws. So
Oh,
if they will satisfy, so it will come out. If there is no ordering, so let's say if I put a sample which is amorphous in nature, so I'll not get any peak. Okay,
no,
so you are not really bother about the internal atomic arrangement, or you don't have to make it really align with that. So in some cases you have to do, if you have a single crystal. So in single crystal you have to be very particular about the orientation. So in that
yes,
case
sir.
you have to do some certain alignment. But if I have a polycrystalline material, normally you don't bother too much about the how you mount your sample, because you will have always certain number of planes which will satisfy the Bragg's condition.
Yes, sir.
Okay.
Thank you, sir.
Hmm. Any other question? Okay, if not, so thank you. So then we will meet Monday again. So I'll stop sharing now. Okay, thank you.